Okay, in the first part of this lab, we want to look at the magnetic field of permanent magnets. I've got two permanent magnets here. I've zoomed in a lot so you can actually see what I have. And they stick together, and we know they're magnetic. Here's a bunch of paper clips, and you see that I can pick up two paper clips, and you see they exert a force on the paper clips, and they also exert a force on each other. Now, we're starting to work with the magnetic field, how to calculate the magnetic field, and later on in class we're going to see how to calculate the magnetic field for currents. Let's see if we can figure out what the magnetic field is for these permanent magnets, what it looks like. Well, how are we going to do that? Well, what we're going to do is a compass. There's a little compass. You see the arrow points north. Of course, when the magnet is in the vicinity of it, it feels a torque actually from the magnetic field of the magnet. Let's see if we can trace that out. Now, what I'm going to do is put these two magnets together to make one magnet and tape them down here. This would be a lot easier for me if Wilson had hands and could help, but he can't. Now, look what happens when I take this magnet and put it in close here. You see the arrow, which points to the north, in the direction of the north magnetic pole, is pointing out. It doesn't point in the direction of that. This is the magnetic field coming out, and here you see that it goes in once it settles down. Now, as I move this around here, you can see that the direction of the arrow is changing, like that. See, now it's pointing opposite of what it was. It's pointing in that direction, and I come down around the end here, and you see that it comes in the south pole of the magnet. Now, if I do that down below here, what I get is a mirror image of what I had above, so it's symmetric. Now, what we're tracing out here, and I'll just draw a few lines. When you guys do this exercise, we ask you to trace out several lines, is the magnetic field lines come out like that and go around, and you can trace this by looking at the arrows, and then they come in like that, and they do the same thing down here. Now, what this is a dipole field. In fact, it's pretty much the same shape of field, but this, of course, is a magnetic field, as what we saw for the electric dipole moment. And what we're going to see is that a dipole field is, in fact, the characteristic basic field for magnetism. Now, let me get some eraser here. Because the next thing we want to do is we want to take these, let me just pull these off of here. Well, easier said than done. So what we had here was we have this type of field for that magnet. What happens if I split them apart? Do I have a north pole in one hand and a south pole in the other? Well, I told you the answer to that in class the other day, and the answer is no. When you split a magnet in half, what do you have? Well, you've got two magnets, each with a north pole and a south pole. So let's take these two halves here, and let me get some smaller pieces of tape and tape them down, and see if we can decide what the field looks like when they're separated like this. Whoops. See, if all the field lines come out of this one like it was a positive charge and go into that one. So here we are. We're at the north pole of that magnet. The field's coming out, and I come around, and I come around. It's pointing back like that. and then no, it goes back in like that. So this becomes a little dipole all itself, and same with this one. It becomes a dipole field itself. So the fields here are like this, and coming into the south pole of that magnet, and then coming out of this one and into its south pole. So you don't get two isolated magnetic charges. Magnetic monopoles, as far as we know, don't exist in nature. So when you break a magnet apart, you get two magnets. Now, I'm going to set up something else here, so I'll pause for a minute. Okay, for the next part of the lab, which is actually really a demo, it is fun, I wish you were here to do it, we're going to repeat Orsted's experiment. I described Orsted's experiment somewhat, and you read about it in your book. What it is it shows that an electric current creates a magnetic field. As I said before, this is probably one of the most important discoveries about magnetism. It links electricity current on one hand with magnetism. So what do I have here? Well, I have a battery, well, two batteries hooked up in series, and I have a wire so that when I close the switch to press the button here, current will flow out of the positive terminal, that is the conventional current, through the wire and into the negative terminal. What I'm going to do is I'm going to put this wire close to the compass and see if the current somehow affects the compass. Now I've got to tape this up here because I only have two hands, so I'll pause again and then we'll come back. Okay, I'm really zooming in now. What I've got here, let me get something to point with. Here's, of course, or I have two compasses. I have this compass here right underneath the wire, and I have this compass here far away from the wire. Now, the current in the wire, you can't see the battery, but the current is going in this direction, like that, across the wire just above the compass there. Now right now there's no current running in there, I should say, because I'm not holding down the switch. But watch what happens when I hold down the switch. The compass right now is pointing north, like compasses do. Both of them are pointing north. But when I push down the button, which I will do right now, big deflection on the compass near the wire. Notice now it's pointing perpendicular to the wire, whereas before it was parallel to the wire. This one just made a slight wiggle. It didn't really change orientation. Let's go back. There, I'm not running any current through. Now let's run some current through. Now remember, the arrow on the compass points in the direction of the magnetic field. So what this is telling us is that underneath the wire, the field created by the wire, and it's pretty obvious that something we're doing in the wire here creates a magnetic field, points to the left as I have it oriented here. Now what would happen if I put the wire underneath the compass? The current, remember, the field pointed to the left when I had it underneath the compass. Let's see if I can yeah, there. I'm going to have to hold it with my hand, or otherwise it'll fall off. But now I have the same situation. I have the arrow parallel to the wire, and right now there's no current running in the wire because I'm not holding the switch down. But when I hold the switch down now, the arrow's deflected, but look, now it goes to the right. It goes the other way from when I had it, when I had the compass underneath the wire. Now, if you could map this out in three-dimensional space with a much more sophisticated measuring technique here, what you would find is that the current goes around the wire. I have a two-dimensional plane here, and the current goes in here, or I'm sorry, not the current, the magnetic field comes in here and it comes out over on this side, so that it goes in a loop around the wire. Now we're going to work this problem out today using the Biot-Savart law for currents, and it's one of the fundamental results for magnetic fields. Now, in the lab, you're asked, looking at this fact that we have magnetic field going around a wire like that, if you could come up with a right-hand rule that describes that. And it's very simple. It's something that we're going to use quite a lot. I said that the current is going this way, like that. And we see that the magnetic field goes around like this. My hand is way too big for this, but I'll try to put it in here where you can see it. The right-hand rule for figuring out the direction of the current, of the direction of the field created by a current, is you put your thumb of your right hand in the direction of the current, and your fingers wrap around in the direction of the field, which actually works here. Now let's try something. Let's test this. Let's switch the direction of the current, and I can do that just by changing the plugs on the battery and not upsetting my wire. Now we should have a field that, set this up again, the field should go the other way, because now I have current going the other way. And I think I've messed up this whiteboard by writing on it. No, it's okay. Now the current's going the other way. Current is going this way now in the direction of my finger, and that means that when the compass is below, the arrow should point to the right. And lo and behold, it does. The field is now going the other way. My right-hand rule, thumb in the direction of the current, fingers wrap around in the direction of the field. Let's test it one more time by putting the compass on top of the wire, and now it should go to the left, and yes, it does. So, like I said, this is a problem that we're going to look at here later in class today, and we'll figure out how to calculate the field for a straight wire segment. Now here's the last part of the lab, and when we do this in class, I always ask students, have you ever built an electromagnet? And I'm always surprised by the number of students who have never built an electromagnet. It's very easy to do. You take a source of EMF, a battery, and you take some wire, and you wrap it around like a big heavy nail like this. Now, how can we show that this is in fact a magnet? Well, let's get a bunch of paper clips out here. Get more than that. Right now, there's no current running through it. It's only a little bit magnetized, and I'll explain that to you here in a minute. But when I run current through this by pushing the button, whoa, I get a really strong magnet here. Very strong, even stronger than the permanent magnets we were playing with. So something's going on here to create this magnetic field. I know when I was a kid, I must have been 9 or 10 years old, I heard about electromagnets, and my dad he loved hunting, and he had all these big flashlights, and I think I stole one of his 12-volt batteries and got some wire and a big nail and made a really nice electromagnet, which was just a lot of fun. But let's see if we can understand the field of the magnet. Now I'm going to lay this down a little bit differently here so that we can understand how this works. And I'll tape this down. Now, what we're going to do is we're going to sort of probe this field with the compass like we did with the permanent magnets, and see if we can understand how it works. Now, the way I have this set up, remember the compass, the arrow points in the direction of the magnetic field. which comes out of the north pole of a permanent magnet and into the south pole. So let's put this up here and see if we can figure out what it is. Well, it's going in, when I'm holding the button down here, and you see that I have a pretty strong magnetic field there. Let's see what we get up here. And the field is coming out up there like that. Now, as I look in the region around the nail, as I move the compass like this, you see that the arrow is starting to change directions like it did for the permanent magnet. Now it's pointing opposite of what it was originally, and then it comes back into the south pole. If you trace this out, you would have a field that came out up here like that, and then down around, and then in like that. And of course, that's the same field as a permanent magnet. So if you replace this with a permanent magnet, you'd have the same dipole field. We're going to be looking a lot at dipole fields. Now, a couple of things about this particular setup here. First of all, this is called a solenoid when I have a coil wrapped around a wire like that. We will use Ampere's law to come up with some nice equations that describe the magnetic field produced by a solenoid. We'll be particularly interested in what goes on inside the solenoid, because that's where the magnetic field is the strongest, as it comes up through here. And in fact, that's that is one of the particular geometries that will give you a uniform magnetic field, as we'll see, and quite strong. Because this is something interesting. If I take the nail out and I just have the coil, what we'll see is that also produces the magnetic field. It's the current that creates the magnetic field, as we'll see. Now, oddly enough, it's pretty weak, isn't it? It's not very strong at all. I know I couldn't pick up a paper clip with it, and it barely deflects the compass. But it's there. Now, some magic happens when you put in a nail. Now, with the nail in, with the nail in, I get a really strong field, much stronger than without the nail in it. So what is going on inside the nail to enhance the magnetic field of just the coil, which is quite weak? Well, the nail's made primarily of iron. Iron is a substance that's called ferromagnetic. In fact, ferromagnetic substances are named after iron. And what goes on inside a piece of iron, if we just draw a little picture here, is the atoms of iron are like little magnets. And most of the time, they point in random directions. There's North Pole, South Pole, like that. This is the way the electrons behave in an atom. Now when I come along and I put even a fairly weak external magnetic field created by the solenoid, the coil, all of the iron atoms line up with that. They're like these little magnets inside a field. They'll line up. Then their fields all add together, and you get a really strong field in combination. So that's an interesting fact about permanent magnets. We're not going to spend a lot of time talking about magnetic materials, but you ought to know how a ferromagnet works. Okay, that's done, the end of the lab, or more of a demo. So let's get started now with how you calculate these things.